Sorry to hold you up.
No worries. Okay, great. So for the second talk of today, we're going to have Chris Jung. Chris has done some really great work in the space of multi-calibration and related topics. Graduated from UPenn in his postdoc at Stanford.
Thank you, Michael. Okay. Thanks everyone for just joining us or joining me. Today I'm going to talk about robust multi-valid uncertainty quantification, and probably have no idea what I mean by robust or multi-valid or uncertain, and how to quantify. Hope you'll what I mean by these things. And the goal of my goal is to not to kind of bombard you with all the low-level details, but just hopefully you can walk with high-level ideas and see the connection between multi-calibration and uncertainty quantification. So that's my goal. And this is joint work with Osbert, Varun, George, Ramya, Aaron. I think within here, only George is here, but yeah. Here's a map of the talk. I only have 30 minutes, so I should try to be fast. First, I'm going to kind of tell you about what I mean by uncertainty estimation and how conformal prediction tries to capture what it, in terms of conformal prediction kind of solves the uncertainty estimation. And then I'm going to try to tell you how multi-calibration comes in, and it can help us try to improve the guarantees of the vanilla conformal prediction. And then I'm going to consider both the stochastic setting, meaning there is some underlying fixed distribution, and then the adversarial setting, kind of like the sequential setting that Dean was talking about. So let me first tell you what I mean by uncertainty estimation and how conformal prediction comes into play. So nowadays, we have all these crazy kind of predictors. Like I've just simply put neural networks, but given these kinds of black box models, we want to be able to quantify how confident the model is about its prediction. Like the phrase I like is, you want to be able to know what the model doesn't know. That's what I mean by uncertainty estimation. And one way to do that, capture this uncertainty, is by coming up with a prediction set so that it contains a true label with some probability, let's say 95%. So here's an example. Like maybe if you're really sure that it's a fox squirrel, you only have just one label. But for other things, maybe you're not so sure, so you have a lot more labels, and you hope that the true label falls in this set with probability 95%. So that's a classification setting. You can also do that for a regression setting, where you come up with some kind of interval around some number. So you have a lower bound and an upper bound. And let me now tell you how conformal prediction works and how it comes up with such a prediction set. And the basic underlying idea is to leverage what they call non-conformal score, noted as SHXY. And it basically kind of captures how well Y conforms to our prediction HX. It's kind of, for me, it's kind of hard to understand what that actually means. I just think about it as, how surprised are you to see this label Y given your prediction H? So the higher this value is, the more surprised you are. So yeah, when I see S instead of score, I actually think about it as a surprise. Big number, you're surprised. And now what they do is, given this one single number, you set a threshold T, so that these are all the labels you're not too surprised to have observe, given the model H. So here's some example. In the regression setting, you can maybe capture how surprised you are to observe Y by seeing how far Y is from your predictor HX. So the further it is, you're kind of more surprised. And given that, and if you set the threshold to be T, the interval will be simply this interval that's T apart from your prediction H of X. And there's another score you can kind of use that's normalized by how uncertain about your predictions on specific X. But there are a bunch of all these things. And today, my goal is not to come up with these things, but take these kind of scores as given to us. So given a conformal score, my job is to simply come up with T so that it has some kind of nice guarantees. So now we're not going to actually talk about how these conformal scores are implemented, but just simply take them as given. And originally, this is the goal that we set out to achieve. we want to find T such that over the randomness of the data, X, Y falls in your prediction set more than 95% of the time. So that was the goal. But just from the way we have constructed this prediction set, now it's simply finding T such that S is less than T 95% of the time. And this is basically a quantile estimation now, right? You want to find a 95th percentile. So and then this is how the split conformal prediction method works to find such T. Obtain a fresh new data set D that's not used to train your model. And look at its empirical CDF of your conformal scores. And now take the 95th percentile from the CDF and use that as T. And by this concentration, you can kind of argue that this empirical 95th percentile should be close to the real 95% quantile. So this is how the vanilla split conformal prediction works.
So the point that given T, you can figure out what is the interval because you are given the
Exactly. So just to repeat Mega's question, once I find T, I can use this T to build a prediction set because I know what the conformal scores look like. But I'm going to be agnostic to what the implementation of those conformal scores are. You can do a little bit fancier things. Suppose you have this joint groups. So point can belong to only one of these K groups. And you want to guarantee that for every group, you want to come up with some threshold TG such that you have the same kind of like 95% guarantee. And in this case, what they do is come up with a threshold by simply looking at the data set, conditioning on the group, and look at its 95th percentile quantile, and to use that as your threshold. And that works to give these kinds of guarantees. Any questions up to this point? This is a very quick just tutorial on conformal prediction. Now I've talked about what I meant by uncertainty estimation and conformal predictions tries to solve that problem. I'm going to tell you how multi-calibration comes in to help us improve the guarantees that I've kind of described to you. And I'm going to do that by just by going with this cartoon kind of example. So suppose a patient comes to a doctor and doctor tells you, hey, given your features, my prediction on your expected disease severity is some number H of X. And the patient wants to know like, oh, how sure are you about that actual prediction? And maybe doctor knows a conformal prediction, so she has come up with this kind of prediction set, this interval, so that the H of X, the real disease severity falls within this interval 95% of the time. But let's try to actually really think about what these numbers mean and what I meant when I said 95%. So the guarantee that I gave was this. One thing to note is the randomness is over the entire population, right? It's not for that specific patient, but when I do this for all these populations, 95% of the time, the true label is going to fall in that prediction interval. Ideally, what you want is not averaging over the entire population, but for each individual conditioning on X and not, you want the Y to really fall in the prediction interval 95% of the time. But unless you make a parametric assumption about how the data is being generated, this is impossible to do. So doctor tells the patient, hey, it's actually a marginal prediction interval, meaning I'm averaging over the entire population. And the patient might think this then. It's like, there's a very easy way to cheat the system. What I can do is for the 95% of the population, I give them the entire unit interval. And for the remaining 5%, I just come up with the empty interval. This is going to satisfy the guarantee that doctor gave to the patient, right? So that's one really easy way to cheat without really knowing what the distribution really looks like. And so the patient complains to the doctor. It's like, oh, I'm actually this part of a demographic group that's only 5% of the population. Can you give me something more meaningful for people like me? And maybe maybe she does belong to all these groups. Maybe that's described by age, race, and gender, all these kinds of things. But things to note is that these groups are not disjoint anymore. She belongs to multiple groups at the same time, unlike the disjoint case. So, but maybe still she comes up with some conformal score threshold for each of those kind of groups, even though it's not disjoint. What can she do in that, if that's the case, while wanting to still give some kind of prediction interval such that conditioning on each of those groups, it's more than 95%. For the first group, maybe this is the interval the doctor gives. Maybe for the second group, this is the interval the doctor gives. For the third group, maybe this is the interval the doctor gives. So although the patient belongs to 3 groups simultaneously, the patient has received these 3 prediction intervals, and how is she supposed to understand these 3 prediction intervals together? Maybe the best thing to do while getting that kind of guarantee is just take the union of all these prediction intervals in this case. So this is like what this paper does. But if you kind of do that, this is a very conservative thing because you're always taking the widest interval possible. So oftentimes, actually, I'll show later, empirical, you always overshoot and cover more than 95% of the time if you do this kind of approach. So in what ways can we do better? And 2 ways for improvement. And then this is where we actually really leverage the ideas from multi-calibration. So we want to come up with a single prediction set or a single threshold for each point such that it is still valid over all the groups, meaning this is what the conformal prediction said. You came up with these different TG1, TG2, TG3, and you took the union of those prediction intervals. But maybe what we want to do is instead come up with some number for each individual such that its coverage is actually, instead of being more greater than 95%, it is actually very close to 95% for all the groups. So I'm coming up with a single number for each point, each person. That's the first thing that we want to improve on. And the second thing is we want these estimations to be calibrated. And what I mean by calibration is this. And then this is to kind of prevent this cheating from happening. What we want to guarantee is every time we use some threshold, f of x, in this case, v, even when we condition on all the possible threshold, one specific threshold, we want the guarantees to still hold true. And this is going to prevent people from doing this thing because you're going to have to condition on the whole interval. In that case, this is always going to be 100%. You also have to condition on the case where you're used to empty set. In that case, this coverage will be always at 0. So, and this kind of calibrated quantile estimation will prevent you from being able to do this kind of cheating.
Sorry, what was your definition of calibrated?
I was actually in the next. So this is what it means to be calibrated. So let's try to actually plug in to see if this thing satisfies this calibration definition. I have used 2 intervals, entire interval, empty interval. And then now I have to use an entire interval. This is going to be 100% because it always covers. Empty set, if I condition on the empty set, it's always going to be 0. But I want to be able to come up with a way so that even when you condition on which thresholds basically you have used, it's still very close to 95%. So combining those 2 things, you should be reminded of multi-calibration. So this is kind of what multi-calibration looks like. Conditioning on your prediction value, f of x, and conditioning on the actual groups. You want this value to be close to v. Same thing kind of happening. Conditioning on your quantile prediction, f of x, and also the groups. You want your coverage to be approximately 95%. So this is now our goal. And we're going to assume the range of this function f is finite, but not a big deal. So any questions up until this point? This is the main thing that I want to kind of everyone to walk away with, that you can do this thing. I'm not going to really have time to show you how to do that. So those are the ways in which I'm going to try to improve the guarantees. And let's jump into the stochastic setting, meaning there is some underlying history. Yeah, question.
because now in some sense so then you're bypassing the impossibility results by how you're conditioning. And so this will be possible to do without parametric assumptions.
Exactly. So I'm not making any parametric assumption, but I want to still get closer to the case where then, yeah.
So it's sort of as close as you can get before the hypothesis.
And I'm hiding some stuff, but I think will be a little bit clear in the later. So this is the goal I said I wanted to do. But once again, when it comes to predict scores, private. So thinking about this problem, I'm just simply going to focus on this problem. And let me describe this thing, what I call quantile calibration error. It should remind you of multi-calibration error. So I'm going to define a quantile calibration error of some function f on some group G. And it's defined in the following way. I'm taking some weighted average. And what am I taking average of? Some square thing. And this basically measures how far this value is from your target quantile Q. So you want this thing to be very close to Q. So in essence, this quantile calibration errors measures how far you are from the original goal I said. And why do we like this? Because if this is less than alpha, you can guarantee for all group G and possible value V that F can output, the following holds true. And this is where I wanted to, what I meant by I was hiding something. You don't want this. Imagine a case where group is like all singletons. I should still not be able to give any meaningful guarantee. And hence, like you need to normalize this by the measure of the group. So first, in this stochastic setting, we came up with two algorithms. First is what we call batch MVP, batch multivalid predictor. And it basically kind of gives the guarantee that I said we want to give. And the algorithm is very similar to the multi-calibration algorithm, where you're iteratively finding some group G on which you don't have that guarantee and the level set V, and you somehow patch this error. The second thing is a little bit weaker version. It's kind of like multi-accuracy, where you're not conditioning on your f of x, but you still, just when you're conditional on G, you want this to be very close to your target quantile. I don't think I have time to talk about how we do this, but yeah, let me just flash the algorithm. So yeah, you're always finding some V and G in the same way, kind of how multi-calibration works.
Question. So when you generate these sets, is it just, should I think about these as like symmetric things? Like I have some prediction new, and then my set is like new plus error minus error.
I think that's a good intuition to keep in mind, but I think it really depends on the conformal score, because it's possible that maybe conformal score, like you have it such that, actually, is it always going to be symmetric? I'm not sure whether it's always going to be symmetric, but that's a good kind of mental image to keep in mind in terms of how conformal score translates to predictions.
Because I guess I was just confused because like it seems like this is like this boosting style algorithm.
Yeah, it is. Yeah.
Calibration, but just like the function you compute, now you need to output a set.
I'm outputting actually simply just V's, right? I'm calculating f of x, and once I give an f of x and the conformal score, it tells you how to come up with a prediction set. So those are kind of two separate things.
Okay.
Here's what the algorithm looks like for the non-calibrated version, but I don't have time to talk about it. So here's an empirical result. The blue one is when you just do the split vanilla conformal prediction. So you don't really worry about groups. This purple one is where you do that widest interval kind of thing. So even though they're disjoint, you take the widest thing. And as you see, you want to be close to this target coverage, but they tend to be always kind of overshooting. But whereas our approach, they're always kind of very close to this 90% quantile that we wanted to. Oh, so the data is on US Census on, I think, just the California. So, and then the actual prediction task was to predict the income. And then you come up with conformal, I think, score. I think we simply use that like the difference. And so you always come up with like, oh, I think your predict income lies between these two this interval. And this is the target coverage we get depending on which algorithms we use. We also calculate the size of this prediction set because we want these things to be as tight as possible. And because the split conformal methods, they always kind of tend to overshoot. Their prediction set sizes are usually bigger than their sets. What is that?
And like, why is like everything on the y-axis are huge numbers?
Oh, because it's an income. So like, I don't know what the actual underlying range is.
But it's the set size, right? Not the.
So I use the set size, but it's, I think, measuring the actual interval. And I've only kind of covered the group conditional kind of thing, but we want to be able to measure this kind of calibration kind of thing too. There are things that are not really calibrated. Batch MVP is the only one that we actually give theoretical guarantee that it will be calibrated. But surprisingly, the group conditional one seems to have pretty low calibration errors. So the doctor now gives this more multi-valid prediction interval kind of thing, just one prediction interval, and she can actually average over any of the group that she belongs to and the prediction each of these groups have received, and it's still a valid 95% coverage. Any questions? Those I think we have.
Can you repeat the question?
So there's sort of after split conformal, there are a bunch of approaches which do like leave one out conformity scores. So leave out parts of the population scores.
Yeah.
I'm not sure if they directly extend to this kind of condition guarantees.
My understanding is that they don't all, and then I think one nice thing, one kind of annoying thing about those approaches is that like you have to, the computational time is a lot. Yeah. Yeah, exactly. But whereas our thing is simple, like it runs very fast.
Yeah, I asked simply because in sort of the unconditional settings,
Yeah.
that's less conservative than the split conformal.
I
So
see.
it comes at the computational
I see.
probably don't want to.
Yeah. We haven't, but would be a very valid baseline. So let me do adversarial. So this is a setting like have like a underlying distribution. Often conformal prediction it works under this exchangeable assumption, meaning past looks like the future. But like here's a Franny Carton saying that like I got this gift based on your previous wish history, but now he's kind of a grown up and but still getting this kind of gift maybe he wouldn't enjoy nowadays. Anyway, so here's a setting. Each time adversary comes up with, I'm not going to have time to talk about what I mean by smooth distribution, but adversarially chosen some smooth distribution over X and Y. The learner gets to see the actual feature, come up with some prediction set with some target coverage in mind. Sorry, I used Q but here before, but I'm using 1 minus delta. And then after the giving that prediction set, the learner actually observes a true label. Once again, you can actually describe this as an online quantile estimation kind of thing. It kind of, you just have to kind of extend some ideas from this previous paper. Looks kind of like you're running some exponential weights on the group and the level sets. And caveat in this case is that it only works for a finite collection of groups, although Smega will kind of hint at how you can actually, we have new results where we can actually handle infinitely many number of groups. So what is the guarantee that we want? We want the empirical coverage that we have seen so far to converge to our target quantile. So look at all the rounds on which X belong to some group G, and all the rounds where our quantile estimate was approximately I over n. Within all these days, we want whether or not our quantile was close to this 95% quantile is approximately something like this. Once again, square root dependence on the size of this thing. Don't have time, so I'll just flash some of the experiments we have. We compare it in the IID setting, so no distribution shift or anything. MVP seems to be a little bit closer to the actual 90. MVP is the our algorithm, and even the prediction set size, it tends to be a little bit smaller. We also introduce some distribution shift, and there is some other split conformal thing that can handle these kinds of weighted distribution shift. We compare to that baseline. We seem to be very close to 90, maybe prediction width about the same. We do this for trying to calculate, understand the volatility of stock prices. We compared it to another kind of paper. These are the results. ACI is the other one. This is ours. A little bit kind of different behavior, but both of them get very good target coverage. But their thing doesn't really give any group guarantees. So once you kind of come up with these different groups, MVP, our thing is very close to 90%. Their thing seems to be undercovering. We consider another setting where very artificial, but conformal scores are always kind of increasing. Their thing seems to be actually doing what I described, where you're always kind of outputting the biggest thing and empty set kind of thing. Our approach seems to be follow more exactly kind of what's actually happening for the distribution that we have to increase in conformal score. Anyway, so the doctor can give this kind of prediction interval that's multivalid even without distribution assumption in this adversarial setting. Yeah, so I think I just wanted to say inspiration from multi-calibration. So it actually extends beyond this quantile. You can do it for some other properties. I think George maybe will be able to talk about that in a couple of days. And then now I should maybe hand over to Sumega in a couple of minutes, where we come up with a way to be able to handle these infinite number of groups in the online setting via some oracles. These are the papers, actually lecture notes written by Aaron. That's very helpful. And that's it.
Any more questions for Chris?
For the experiments, I guess is the main qualitative difference between the split conformal and this algorithm, that the split conformal just takes the union overall groups, whereas you're doing something that's
Yeah.
on the cap.
Yeah.
That's what the thing that buys you like the big.
Thanks.
What?
Are we allowed to talk right now?